Okay, so it's a great pleasure to welcome Wolfgang Ziller, who will speak on curvature homogeneous metrics.
Okay, thank you very much for the invitation. Can everyone hear me?
Yes, perfectly.
Yes.
Okay. Okay, thank you very much. So I'll talk about a topic that I fell in love with a while ago, and I want to tell you why and tell you some of the recent results. Let's start. So first, some definitions. Certainly everyone knows what homogeneous means. So it means for any 2 points in the manifold, you have a global isomety which takes one point to the other. And of course, a local version also. You take 2 points P and Q, you have an isomety from the neighborhood of P into the neighborhood of Q. That's something local, and what you keep in mind, in general, there's a big difference between local and global. So here's an example, one of my favorite examples. Take S3 cos S3 divided by a real line in the maximal torus. And if that slope of that line is irrational, you get something locally homogeneous, but it's not a curvature tensor Riemann manifold. So it's not, it's only local. So local and global you have to keep in mind. Okay, so now it's come to the main definition. The manifold is called curvature homogeneous. So that's what I want to talk about. If for any 2 points, I don't have a global isomety, but only isomety of the tangent spaces from P to Q, such that it respects the curvature tensor. So it pulls back the one at Q to the one at P. So all curvature tensors are the same from point to point, but there are no local isometries. And the manifold doesn't have to be complete either. It's just a pointwise definition if you want to. So what can I say about that? Let's see. Well, first, some remarks. Of course, if the dimension is 2, that's the same thing as constant Gauss curvature. So here, there's nothing interesting. If the dimension is 3, there's an interesting equivalent definition, which says that the Ricci tensor has constant eigenvalues. So that's a special capitalization dimension 3, which I like. It's a more geometric, if you want to, constant Ricci eigenvalues. So that's in dimension 3. The question that Isidor Singer asked a long time ago is kind of a natural question. Is every curvature homogeneous manifold homogeneous, or at least locally homogeneous? Or how can I tell something is homogeneous? This was one of his earlier papers. This is Isidor Singer, the famous one, right? He wrote some very nice papers on homogeneous geometry in the beginning. Let's see, can you see me too? I don't see
Yes,
myself.
I can see you.
Yes.
But
Yes.
So this was a question that was motivated by a paper that he wrote in 1960. So here's what he did in the paper. Namely, the question was, how can I tell something is homogeneous? From curvature information. And here's his theorem. So take a complete manifold, simply connected. For any 2 points, you have an isomety, again, of the tangent spaces. But now he asked not only that the curvature is respected, but also many higher derivatives of the curvature. From point to point again, it's a pointwise information. If this is true for all k less than some number, here it's n times n minus 1 over 2, then in fact it's homogeneous. And since it's complete and simply connected, globally homogeneous. This number n times n minus 1 over 2 is the dimension of the orthogonal group. That's where it comes from. And this created an industry afterwards to see, well, first a remark that this is a proof, which I think is the only proof I know, that if you have something locally homogeneous complete, then the New cover is also homogeneous. Kind of surprising that there's no simple proof of this fact. And of course, Singer's theorem says something local condition, and it says the answer is if it's complete, that it's homogeneous, if it's complete and simply connected. So that's an interesting corollary. Maybe someone else knows a simpler proof than Singer's theorem, but I haven't seen one. So maybe someone does know something. So let's just create an industry then. What's the best value of K in terms of the dimension? N times N minus 1 over 2 is very large. Can one do better? And there is a remark of Gromov in one of his famous books that it's linear. The best is linear, certainly. It's 3/2 N. And in low dimension, you have a very nice answer. So in dimension 3 and 4, it's 1. So that means if I can match the curvature and its co-derivative, then it's homogeneous. Okay. Then in high dimensions, there's a sequence of papers that try to determine the best value. Doesn't get very interesting, except for dimension 3 and 4. Okay, so that was his paper. And at the end of the paper, he asked this question. Well, is it sufficient to match the curvature tensor to conclude something as homogeneous? And the answer is no, of course. Otherwise, I wouldn't give my talk. Let's see. What do I want to do first? Okay. So we have it. The next definition is to kind of formalize that in a way by looking at what I want to call a curvature type. Take a vector space and specify a curvature tensor with all usual symmetries. Then I say my manifold M is of type R0. If for Rp, that's the curvature tensor. So if the symmetry from the tangent space to the vector space, so that my model, my type, R0 pulls back to the curvature tensor at every point. Of course, every curvature homogeneous space has a type. So I want to formalize this as a word. Okay. So that's the type of the curvature tensor. And the natural question then is, how large is a set R0 which can be realized by curvature tensors? So for which tensors can I find one? And if I can, how many are there? How large is the set in the space of all curvature tensors? That's a natural kind of question. And that's very difficult. I'll say about that a few things as we go along.
So the question is for a fixed Riemannian manifold, right? How large the set?
No. Take a vector space and look at the space of all curvature tensors. That's
Yes.
Now the question, in that space, how large is the subset in that vector space such that such curvature tensors can be realized, at least locally, maybe globally. So I'm not starting with manifold,
Okay.
curvature tensor. Then I want to find manifolds, but that is a curvature tensor at every point. You understand?
Yes, thank you.
Sure. So here is one theorem, for example, an old theorem by Kowalski and some others, that in dimension 3, every curvature tensor can be realized, at least locally, by some curvature homogeneous metric. Okay. The proof is extremely complicated and messy. I never understood it. It's local. It's very much an open question. When can you have a complete one? And even worse, can you find a compact example? In dimension 3, there's essentially nothing known. I think every three-dimensional compact curvature homogeneous space is homogeneous. We talk about that in high dimensions, but in dimension 3, everything can be realized with interesting open questions. Okay. So there's a talk by Robert Bryant that he gave at a conference in Florence in 22 that I organized in honor of Wolfgang Meyer's retirement. And he gave a beautiful talk on this kind of question in dimension 3. And he formulated this as a certain kind of initial value problem. So in a sense, it's a PDE. That's what Kowalski studied. They are very complicated PDEs. They're hard to understand. And Robert Bryant, of course, saw the kind of the geometry behind it. And he said, take a surface with specified data. Then in the neighborhood of that surface, you can find a metric, which is curvature homogeneous. So kind of as an initial value problem, where the proof becomes much simpler. And then, sorry. And then in his talk, he also gave various examples coming from algebraic geometry, where for special eigenvalues, the rigid tensor, you get interesting examples. So this talk got me very interested. My students are also in this topic. He never published the paper, unfortunately, as often he gets interested in many things and doesn't find time to write things up. But it's a beautiful paper when it comes out, I'm sure. Okay, so this is in dimension 3. In higher dimensions, one can ask the question, what are the abstractions and when do you get uniqueness? So in other words, are there some Curvature tensors which cannot be realized? I want to view that as an abstraction. And here's an old paper, Trecea von Hecke. Take the Curvature tensor of S4 on R4, so just pointwise. This is now a pointwise object. Take the Curvature tensor of CP2 on a vector space, again a pointwise object. Take a linear combination. So this now sits in the vector space of all Curvature tensors. And then they'll show that this is Curvature homogeneous. In other words, does there exist a local example which is Curvature homogeneous with that particular curvature? And the answer is only in the obvious cases, when A is 0 and B is 0. So that's an abstraction. They have other papers where they find many examples which are abstracted. They're quite messy to understand, but that's certainly an interesting question. Can one, in more detail, answer this kind of problem? What's the subset of Curvature tensors that can be realized? Uniqueness is the other question. And here's a very nice theorem of Trecea and von Hecke. Let your type, your curvature type, so your model curvature, be that of a symmetric space. So let's say right now an irreducible symmetric space. Again, like I said, that's my curvature tensor on a vector space. And now the theorem is that, well, if that can be realized as a curvature tensor in the neighborhood of a point, which is curvature homogeneous, then it's locally symmetric. So uniqueness. So these curvature tensors, they have a unique realization, unique examples. And that proof is really simple. So I just learned that recently. It's beautiful and simple, and I want to show it to you. Well, let me get my pen. Oops. So here's the example. I use a Bochner equation. And this Bochner equation holds for Einstein metrics. So here, the second equation is a symmetric space. And this is my general manifold anchor G. So in both these spaces, I have the same Bochner equation. Okay. So I require that R is equal to R0. So that means these two are the same. Okay. That's what the theorem assumes. The theorem assumes R0 and R are the same. F of R is some complicated algebraic expression in terms of R. I won't write it down, but a priori they must be the same. Of course, the length is constant, so this must be 0. This must be 0. And for the symmetric space, of course, the co-derivative is 0 by definition, if you want to. So therefore, now, of course, it follows that this must be equal to 0. So it's locally symmetric. That's the whole proof. Very pretty. So I want to show that. Now I want to add this Bochner formula holds for Einstein metrics, but one can generalize a little bit where one shows that the theorem holds if it's not irreducible anymore, as long as it has no Euclidean factors. Can you see that last line on your screens? Hello?
Last line I see says it holds for a symmetric space without Euclidean factors.
Yeah, I wasn't quite sure if everything's visible here on your screen also. Anyway, so this is a uniqueness statement. So now let's go back to how do you tell the difference between homogeneous and curvature homogeneous? And again, there were two theorems of Singer, which I want to explain. One, most of you know in some form or another, an old paper by Ambrose and Singer, which you know for Riemannian manifold, with a Levi-Civita connection. So here's a statement. Take a complete, simple connected manifold with a Riemannian metric. And it's homogeneous if and only if there exists some connection, a metric connection, such that the curvature and tensor is parallel. So here R is a curvature of D, and T is a torsion of the connection D. So if they're parallel, then I can tell that it's curvature homogeneous. You know, if it's complete and simply connected. Otherwise, you know it's a camera. And in fact, here's a simple proof of this. Let me see if I wrote that down. Oops. No, I didn't. Well, so let me just say, if the torsion is 0, this is a theorem that we prove in class usually. If you have co-derivative R is 0, then it's homogeneous, it's a symmetric space. So that proof we all know from our courses. And the claim is the same proof of that type also works if you have torsion. And then the metric is locally is homogeneous. So, and then the other theorem that's in a proof, which of course I like in our context here, that to tell is curvature homogeneous, I drop a condition on the torsion, and I take the curvature tensor of the Riemannian metric. So I have a Riemannian manifold, M comma G. R now is a curvature tensor of G, and I want to find the metric connection so that R is parallel. If I can do that, then it's curvature homogeneous. And then if one wants to tell it's homogeneous, again, if one requires that for sufficiently many covariant derivatives, like we did earlier, then it's homogeneous. Of course, I like this here just for the curvature homogeneity, so not the high covariant derivatives. All you need to do is show that the curvature tensor is parallel. Now, let me just first point out that this is actually kind of obvious. Here's a proof. In one direction, use parallel translation, right? So take 2 points P and Q, take a curve from P to Q, and now use parallel translation of gamma to go from TPM to TQM. Since the curvature is parallel in R, of course, that means the curvature is constant along this curve. Okay, so that's in one direction. That's kind of a trick. So it gives you a natural kind of way to compare the tangent spaces as opposed to some fine one. The other direction is also not hard. So take a curvature homogeneous metric. This is again local. Choose a smooth local basis. Smooth local orthonormal basis, because I should have said that, such that the components of R are constant. Right? We know that R is the same at every point. And now I say just realize that in a basis in a coordinate system. Okay. So now R is constant in that coordinate. Now let D be the connection where these basis vectors are parallel. Just declare their connection to be like that. This basis is a parallel basis. Okay. And then use partition unity to collect all the different connections into a global connection, which is kind of confusing, but you should observe that if I take a sum of 2 connections applied to R, it's just the sum. No derivatives with respect to D are involved. Of course, the connection, space of connection is a linear vector space, and therefore I can add, if it's parallel with respect to D1 and D2, it's parallel with respect to the sum. And then you can make it global. So that's a very simple kind of proof of this theorem. Okay. So let me reformulate this now in a way that I like better. It's kind of an algebraic condition. Namely, I claim it's the same thing as saying that the covariant derivative, so the ordinary covariant derivative of the curvature tensor, is linearly related to the curvature tensor. So I claim it's curvature homogeneous if and only if you can find some tensor A skew symmetric to one tensor such that nabla R is A times R. And so nabla R and R are linearly related by this tensor A. So I like this kind of description of curvature homogeneous. And of course, in order to do that, what you do is you simply let A be equal to nabla minus D. Right, choose your connection D that you found in the previous theorem. Look at the difference. If dr, if A is nabla minus R, this is nabla R minus dr. And then nabla R cancels, so dr is 0. Okay. Okay, so that's a description that I like. Okay, so the next concept I want to look at a little bit is, again, having to do with the vector space of Curvature tensors, but not yet with any manifold. So I want to declare the symmetry group of a Curvature tensor on the vector space V. Okay, so just let that be those orthogonal maps from V to V with respect to Curvature tensor. Okay. So, of course, this is, if you want to, you can regard this as a subgroup, subgroup in the orthogonal group, and this group is compact. So you had certain compact subgroups of the orthogonal group, which tell you how large, how symmetric is your Curvature tensor. And I want to make some observations about this group, which I think is very relevant. So now take a manifold M with a metric, Riemannian metric, and choose this connection D so that R is parallel, which we know exists because it's Curvature homogeneous. And then, of course, if I now pull back my endomorphism A from V to the tangent space, the Curvature tensor is respected at every tangent space with respect to these compact groups of endomorphism at every P. That defines a principal bundle, right? So at each point P, so here, what I mean here, say, take an orthonormal basis in TPM and assume that R in this basis is R0. So in other words, I just realize in the frame bundle of all possible no. Sorry. Couldn't find my eraser. Anyway, so in the frame bundle of in the tangent space of P, I look at those frames which give you the same Curvature tensor. Now G, of course, acts on that by acting on the basis. That's a principal bundle. So this principal bundle is an important part of the information of any Curvature homogeneous metric. And one would like to understand this principal bundle. So here's some other observations. First observation is the holonomic group, that's connection G, of course, lies in this compact group, in the symmetry group, because it preserves the curvature. Okay, so if G is small, the holonomic group is small. Next observation is that if the holonomic group is trivial, of course, that means the connection is unique. So in that case, you get a global unique connection in which R is parallel. So that's the nicest case. And now observe, well, that's actually generic. So generic, this must always be true. Namely, if G0 is trivial, R has no symmetries. That's a generic property. G is unique. You get a global paraflame on US clever. So that's a particularly nice situation, which must hold generic. Of course, I'm not saying that Curvature homogeneous metrics are generic, that the Curvature tensor is generic. That's what a separate question I asked earlier. So I'm not saying that. But the type and then the symmetry group is an important kind of question. So now, of course, say, for example, if I can want to specify G, say G is ON, also that's in conceptual closure. If G is a unitary group, and it's the metric is CPN, the student, and G is SPN, and the metric is hyperbolic space. So for large groups, it actually tells you what the tensor is, because they have too many symmetry. The smaller the group gets, the compact group gets, you have more and more freedom. And then one can look at how small is the vector space, which realize that symmetry group, and then how many vectors can I find with that symmetry group. So one can go down with the dimension to understand kind of what are the possibilities for it. Curvature homogeneous, what type of curvature homogeneous metric, and then find these. Okay, so let's now get to examples. My favorite example is the FKM examples, Fayos-Karshner-Münster examples. Where you start with a Clifford algebra, so that means you take K anti-commuting complex structures on Rn, and so that's in other words, a Clifford algebra. And now in terms of Clifford algebra, you define a polynomial on R2n, which is homogeneous on degree 2. So the AIs are used in the last term. So that's a very nice polynomial. And then you look at level sets. And so let M be the level sets for various constant C, such that it's a hypersurface, that's the generic. Then this hypersurface has constant principal curvatures. So it's called isoperimetric. And of course, once the principal curvatures are constant, the Gauss equation will tell you it's curvature homogeneous. So that property is an immediate consequence of this being curvature homogeneous, is an immediate consequence of requiring that the principal curvatures are constant. And now the maybe important observation is that these are the only known compact curvature homogeneous example which are not homogeneous. That's kind of embarrassing. Because people have looked for other examples which are compact. It seems to be a difficult problem. There are many complete ones nowadays. Oh, where do they go? And jump pages. That is not good. I apologize. Here's Karshner-Münster. Here we go. So these are the only compact examples that I said. Okay. I also looked for such compact examples, say among Cauchy-Mann manifolds, and even there it's quite difficult. I did not succeed so far. Okay, the more classic example. In fact, this was the first counterexample to the questions of Singer, whether there are curvature homogeneous metrics which are not homogeneous. And he wrote down a very simple one in R3. Where X, U, and V are the chords R3, usual du dx dv notation, and P is an arbitrary function of two variables. And then the Ricci eigenvalues of this kind of metric is given by the function P in terms of the usual formula, P sub u divided by P. So now, of course, the Ricci eigenvalues are functions of X and U. In their own right are interesting, but in our context, of course, we want to make the Ricci eigenvalues constant, so I just specify P. So if P is like a linear combination of Cauchy and Sinh, F1 and F2 are two arbitrary functions. Of course, then Pu divided by P is -1. So I get Ricci eigenvalues -1, -1, 0. And the metric is complete. And it's also locally irreducible. And it's not homogeneous. So all these things one can prove, and they're not too hard. And the curvature type now, because the eigenvalues are -1, -1, 0, is H2 cross R. So in other words, it looks pointwise at every point like H2 cross R, as far as the curvature tensor is concerned, but it's not homogeneous. Okay. Now, then people studied this kind of question, what do they all look like? These are examples. And there's an old theorem by Van Hecke and and Kowalski from 92, where they studied this question in dimension 3, so three-dimensional manifold, where R0 is of type H2 cross R, just like in these examples. And they showed it has an open dense subset where it looks like that in the above form. But it's only an open dense subset, and they didn't understand how complicated or what the complement might look like. This was a question they asked for a long time. And in their proof, which is very complicated, and unfortunately, you can't really tell. So one of my students, Tom Brooks, he listened to this lecture by Robert Bryant in Florence, and he thought this was a very appealing kind of question when I think curvature homogeneous. And he studied some of the examples in the literature, in particular this early example, and thought about this question, what if R0 is H2 cross R, but how can I tell what the rest looks like? And he figured that out. And it's very interesting. So instead of this metric that Sekigava wrote down, we change coordinates. And the coordinates are much more general. For Sekigava, the coordinates are smooth. Now he chooses XUV, which are Lipschitz coordinates in R3. And he finds a metric in these Lipschitz coordinates. And now I put the functions in a different spot. So this function f here is my first function. This function h here my second function. And I can tell you in a minute what the role of h and f are. Well, they're different than the f1 and f2 in the Sekigava example. Maybe the first observation is that if I let f be 0, so then what you get, what's left over is, so this part here now is only dv squared. So this here becomes dv squared plus du squared. So now collect this part right here. That's of course the usual metric in H2, because this coefficient here, or this coefficient p double prime over p is -1, is just a strange way of looking at the metric. And now the funny thing is that if I look at the metric in R2, in Lipschitz coordinates xu, where h is only Lipschitz, even better than that, it must be isometric to the smooth metric on H2. So that was is an amazing observation. So here's maybe a more concrete condition. So let h be the derivative of a one Lipschitz function. So it's only smooth almost everywhere. So take such a function h, and now I can take a look at again at this metric right here first. That's just h2. Under this very weak assumption, this metric here is isometric to, or can be extended isometrically to the smooth metric on H2. That's his first observation. And
Excuse me, Wolfgang.
yes.
I thought it was my computer. I would have said something sooner. On your screen share, I think your picture appears on top of the slides near the bottom. And so if you could make sure that when you get to the bottom couple of lines, maybe slide the your screen up a little bit so that it's not covered.
Something happened with my screen
Oh,
share.
yeah. Oh, dear.
Happens in again.
Yeah. Oh, sorry, maybe I should have interrupted. Right.
Starting or start broadcast. Why is it taking so long? Ah.
Oh, dear.
No. I'm sharing now. I don't understand what's going on.
Yeah, we're not seeing it yet. We're just seeing something that says you're sharing. I'm sorry, I think my interrupting may have. Sorry for that.
Let me do it once more. I did something wrong. I'm assuming I'm supposed to say okay now. Now I should say start broadcast, I guess. 3, 2, 1. Something happening?
It's still, which is still just seeing the thing that says
Screen broadcast.
screen broadcast, but not the actual slides.
Of course, it's terrible. Share screen and tell me. I guess do it on my laptop instead. I'm so sorry.
If you try clicking on the slides directly, it may be that
How about this?
now we're seeing, now we're good.
That
Yeah.
was a problem. I'm just click on the slides. Okay, I'm so sorry, but thank you for telling me. So this was his observation. You can extend the Ziller metric if you allow Lipschitz coordinates. With the very weak smoothness conditions on the coefficients or the functions, then the claim is you can extend the metric smoothly. So you start with am I writing or not? You start with f equal to 0. That's simply h2 cross r in finite coordinates. And now I twist it by adding an f here, like a twist, a warp metric if you want to. A very funny kind of warping of the metric with a C11 function. And now it becomes locally reducible. It's complete as curvature type h2 cross r, but it tells you what the complement of the Sekigahara example looks like. It's not that bad. And one can also study the geometry of it, what this means, which I maybe don't want to go into too much. Maybe just say one word. I think I have some time maybe. If I look at x constant, maybe over here. So these coordinates is x constant. These are totally geodesic, flat, and complete. Hypersurface, of course, right? So R2 in M3. But these are flat. So it's foliated by flat leaves, by flat R2s. But the foliation is only Lipschitz. Just like the metric. It's a very funny kind of foliation. In this hyperbolic metric right here, you get a foliation of H2 by geodesics, which is only Lipschitz. So that's a trick that Brooks discovered in order to describe the set of all postural metric of curvature type R0. Okay. So what's another student of mine recently looked at higher dimension examples. There you take H2 cross Rn minus 2, and you get you can prove that a similar story holds again, gets a little more complicated. And remember, I explained earlier that for a symmetric space, if it has no Euclidean factors, the metric is unique, it must be symmetric. And if I add Euclidean factors, like in these two examples here, then you have many possibilities. And the space of metrics is infinite dimensional because it depends on two functions of one variable. Okay, so this was recently, and in higher dimensions by my student Jacob von Hook. So now I want to discuss another example that was relevant for what I did recently in joint work with Robert Bryant and Louis Florit. This example goes back to Tsuchara. So he asked the question, well, if I look at hypersurfaces in a space of constant curvature, hyperbolic space or a sphere, which is curvature homogeneous. So the metric is an induced metric from the hypersurface. And he had to assume that n is at least 4 in his theorem. And then the statement is, it either has constant curvature C, those are easy to describe, they're kind of cylinders, or it has constant principal curvatures, for example, the FKN examples, or it is isometric to a hypersurface in H5. So besides the obvious and classical examples, there's one new one, the Tsuchara example. And this example interests me at some point. And in this paper, somewhere hidden in the paper, explains that this is actually curvature homogeneous. Namely, the SO3 acts on this four-dimensional manifold, a homogeneous one, M4 is not compact. And you write down the metric in terms of coordinates T, which is the arc length or the orthogonal-geodesic. Theta 1, theta 2, theta 3 are the usual bases in the Lie algebra of SO3. And the functions that you have to multiply these by are very simple exponential functions. When T0, this degenerates to a very neat surface in H5, and T is complete, and it's defined for T greater between 0 and infinity. So this got me interested in this kind of question. Well, if you assume curvature homogeneous and homogeneous one, how much do you get? So the first answer I obtained in a theorem with Luigi Verdiani, which answers this question in dimension 4. So precisely in the dimension where the Tsuchara example lives. So we assume curvature homogeneous, homogeneous one, and complete. And then we showed that it's either a symmetric space or it's a Tsuchara example. Locally symmetric, I guess. Or it's a Tsuchara example. So it's actually unique also in this intrinsic kind of fashion. Not for hypersurface, but intrinsically. You cannot find anything new in dimension 4 in a curvature homogeneous kind of setting. Now, some of the Beos-Karshner-Münchner examples are some of them are homogeneous one. A few of the Beos-Karshner-Münchner examples are homogeneous one. So in high dimensions, they don't exist. Other compact examples, which are homogeneous one and which are curvature homogeneous. They actually exist also in high dimensions, but only of FKM type. And it seems to be very hard to find new ones, which I've tried for a while, which Luigi and I have tried for a while. Okay, so that's the story of what was known. Then in Tsuchara, he had to assume that your manifold has dimension at least 4, your M, and it was open for a long time what happens when in H4 or S4, so when you have 3-dimensional hypersurface. And this seems to be a different type of problem and much more complicated. Now, maybe I'll just say a little bit in a while why that's the case. So here's some description of the Tsuchara example, which is relevant for my story, for the story with Louis and Robert. It's a kind of a different description of the Tsuchara example, different than the one you find in his paper, which I never understood. Take a Veronese embedding of RP2 in S4, the standard kind of Veronese embedding that we all know and love. Take the unit normal bundle of the Veronese embedding and write an immersion, actually an embedding of R cross the unit normal bundle into H5. For H5, I take the Lorentz model, so it goes into Lorentzian space, 5 plus signs, 1 minus sign. R is defined for S greater equals 0. And here's a simple way to write it down. Cx is a normal vector in my normal bundle, as is my parameter in the real line direction. And the first Oops. The first four here, the line R4, the matrix positive, and here the matrix is negative, Lorentzian metric. Right? Plus signs here and minus signs here. So if you haven't learned this, well, let me just leave it. No. Not large. Okay. Is it small on your screens now? Ah, maybe this is better.
Yeah.
Okay. So the next slide here. So now you can compute if you want to, if you the first R4 is a positive sign, so you get G1 has unit length, Cx is orthogonal to G has unit length. So this lives inside the vectors in Lorentz space of length -1. That's a Boboric space. That's a Zuccata example. It's actually quite simple, much simpler than what Zuccata had. And the proof that these are the only ones also becomes much simpler with modern methods, which Louis and Robert have described in our paper. So here's a new example, which is relevant for the work we are doing. And now the example goes into H4. So it's a three-dimensional example. So it's now M3 in H4 instead of H3, instead of so the open question where it was not known whether what they look like. So here's a simple example which is similar to what Zuccata had. I take a Clifford torus now in a 3-sphere radius one. And using this Clifford torus, I write down a similar expression. So G is my Clifford torus, Cx are my normal coordinates of the Clifford torus. And this lies in H4 in the Lorentzian space now again. So this image F has length -1. But the induced metric on the surface itself, on this three-dimensional surface itself, has on the surface G itself has is simply flat. Whereas in the Zuccata example, it was at curvature 1. Okay, so now let's see what they all look like. Okay, this is the ones that you can write down easily. And here's our theorem. So this we did recently, just appeared on the archive. The question is, let M3 be a manifold which sits in H4, S4, and H4. We don't assume Clippinos or anything, just if you want a local kind of question, and later on one can ask the global question. So you have a hypersurface locally with constant Ricci eigenvalues. Remember in dimension 3 that's equivalent to saying it's Curvature homogeneous. So I want to formulate like this. Then there are the following possibilities. First one is a very old one by Cartan, which is a homogeneous example. These are the orbits of the action of SO3 and S4. If you've seen that before, they're kind of very natural. It has constant principal curvatures, so it's curvature homogeneous. Ricci eigenvalue is constant. That's an old example. The next one is the one I just described. So unit normal bundle of the Clifford torus in H4. And it turns out this three-manifold has Ricci eigenvalues -2, -4, -4. And the next example, and now comes the interesting one, that's kind of a simple one. There exists a one-parameter family of hypersurfaces in S4 and H4. It has only finite symmetry groups. So A was homogeneous, B had T2 symmetry for the three-manifold, and now it's only a finite group. And the Ricci eigenvalues in each case, depending on the case, are 2, -4, -1/4, -1/4 for S4, and -2, -17/4, -17/4 for H4. So it turns out that the particular eigenvalues, the Ricci curvature that you specify, seem to have a very strong influence on the geometry of the examples. which also was true in Robert's work that he presented in Florence 4 or 5 years ago. And there's one more, namely a hypersurface which does have symmetries, a circle worth of symmetries. You take this family that we discovered in C, and you take a limit as C goes to a limiting value where they exist. Then you get something, and then again a hypersurface, but now it has a circle worth of symmetries. And this last case is easier to describe than case C. So let me write that down a little bit, and then say more about the properties, the proofs and the properties a little bit. Because I then want to ask this kind of local, and then I want to ask something more global also. So maybe the first remark is only A and B are complete. These new examples we found in C and D, they have singularities, but they're very nice singularities actually. And the example in D is an algebraic hypersurface. That makes it particularly interesting. In C, we don't know yet if that example is algebraic or not. But in D, you can write down the polynomial, which I'm going to write down in a minute. So here's the example of symmetries. Start with a disk in polar coordinates. Write down the 5 coordinates which lie in S4 in terms of sine and cosine. Notice the last coordinate is restricted. Right, this coordinate here. If it's to be positive, r must be less than r cosine squared 2 over 3. Otherwise, the last coordinate is not defined. That gives me a disk. R equal to R0 if you want to is the equator. And now reflect it, and you get a sphere. So each half, northern hemisphere and lower hemisphere, is described like that. For the lower hemisphere, I put a minus sign in front of here. Where's my pen? I put a minus sign and I get a 2 sphere. It's not smooth along the equator, but it's still a nice smooth immersion. Sorry, it's smooth. It's a nice smooth immersion, but the metric degenerates along the equator, and the mean curvature goes to infinity. That's how you can see the singularity. It's kind of like the bugle surface in R3, right? Where you look at a constant curvature -1 R3, you get our bugle surface that has singularities along a circle in R3 along the xy plane. You reflect it, you get a nice curved, a nice hypersurface in R3 with curvature -1, singularities. This is of a similar type, except for now the curve in R3 that you would get for the bugle surface becomes a torus knot in this code, in a certain torus inside S4. It's now a torus knot, so it's more complicated. Now what I do is I take the normal bundle like before. I take my map. Sorry. Well, that's what I said earlier, right? You take your surface in S4 to get the 3 manifold. I look at the normal bundle. I can't get my pen. Annotate. Here we go. Right here, this was plus or minus 1. So I said. So now my M3 is gotten by taking G, then define F as the norm in terms of the normal bundle, right? So I describe here now the image of this surface inside S4. And that's algebraic. And here's the polynomial. Let me see if I can make it larger again. So here's a polynomial. Can you see that?
Yes. Oh, that's good. Oh, that helped a lot.
Okay. So it's a degree 6 polynomial, right? In the 5 variables in R5, complicated polynomial. And the magic is that this is curvature homogeneous. Or it has constant Ricci eigenvalues. That's kind of magic. You would never discover that unless you'd have some kind of parameterization that comes out of your proof, actually, of this main theorem. So this is not something you would come up easily if you just looked for it. So that's the explicit example, right? This was D. That's this hypersurface D. It has circle symmetries, which you can see by the theta, right? As theta rotates, you get your circle symmetries, but not more than that. That's a full symmetry group up to components. Okay, so I have described this example explicitly. And now in the last 5 minutes, let me say I want proofs this main result, the strategy of the proof. So I start with my hypersurface in S4. So I'm going to do it for S4, H4 is similar. I assume it's curvature homogeneous. I assume it's not isoperimetric. It doesn't have constant eigenvalues of the shape operator. It doesn't have curvature, section curvature 1. And then it's curvature homogeneous if and only if the shape operator is rank 2. And the scalar curvature is constant. So forget about the curvature homogeneity. Just look at a 3-dimensional hypersurface in S4. Assume a shape operator has rank 2 and the scalar curvature is constant. That's equivalent to being curvature homogeneous. So from now on, you want to do submanifold geometry. You have this nice submanifold with properties of the shape operator. So what do you do next? You observe that this shape operator, it has rank 2, it has a 1-dimensional kernel, and M is foliated by the geodesics, which are tangent to the null space. These are called nullity geodesics. So you get a nice foliation of M3 by these kind of geodesics. That's a general phenomenon that's well known in submanifold geometry. The null space gives you flat surfaces which foliate your space. So the next thing you do is you identify out the geodesics to a point, and you get a surface, the called a polar surface, which now goes from V2 into S4. And now everything is formulated and proved in terms of this polar surface. Again, a well-known trick in submanifold geometry. And then once you get the polar surface, you define your F as a normal bundle of your polar surface. So if I know G, I know F. So forget about F and only look at G. It's much easier to study. Then one shows that F has rank 2 if and only if the immersion G satisfies that the determinant of a shape operator is constant for all normal vectors, or the embedding G, or the immersion G. That's a strange kind of property, and of course very strong in terms of shape operators. It doesn't have constant eigenvalues, but the determinant is constant. And that's equivalent to what we want to study. So now you look at surface this special kind of property, and you want to determine what does the shape operator look like. So you drive a property and description of the shape operator at points which are not minimal originally. You show that it looks like has a certain form. That form depends on a parameter A. It's very important to determine what the value of A is, which is surprisingly difficult. So what you do is you take the structure equations and use a Cartan calculus, which is much simpler in this context. Takes the usual structure equations, so Gauss and Kodazzi and Ricci equations in the differential calculus formulation, differentiate again. And then what you get is a polynomial of very high order in the variable A, which I want to figure out. And it's kind of amazing that you can show eventually that this value A must be 2/3. And this was kind of surprising. Once you see these polynomials, you're sure this doesn't exist. These hypersurfaces should not exist. This polar surface doesn't. There's no chance it should exist. But this is only done with Maple, right? You have this long list of polynomials of very high order. You want to find some combination which is simple enough where you can recognize something, and you can't do that by hand. So you find a Grabner basis with a tricky kind of ordering. Then you see one polynomial, which you can write down, where you can see what you're trying to prove. A must be 2/3. Once you have that, then you show that the structure equations are define the immersion G, the polar immersion G globally. So you have your shape operators, you have your value A, you know exactly what the shape operator looks like. You have to now verify the structure equations are satisfied. All these things, these last 3 points here, they're quite different and they're long computations, but this is the structure. The last thing one can then do, and which we do to some extent in our paper, you want to then derive global properties of G. So up to now, the whole theory tells you that G exists locally. And that's the usual thing in submanifold geometry. If you know the structure equation is satisfied, it says they're local examples. And here we know that exists globally, and now you want to see, can I find it globally? What does it satisfy globally? And we just saw in the example of the Clifford torus, and in the example of the one with symmetries, the global version has singularities. It's not complete. So one can try to see, well, how about for the examples with no symmetries? What are the global properties of G? And in the paper that is on the archive, we studied that to some extent. But I think I don't want to discuss that. That gets a little more detail that is in the paper, but maybe not too much for this talk. So let me stop right now, and thank you very much for your attention.
Thank you very much for a really fascinating talk. Are there questions? So I was really struck by getting these examples with no symmetry. These are the only known examples without symmetry. Is that right? Or
Some of the FKM example, I think, have no symmetries. And these local example dimension 3, I'm not sure if they proved that, but I think the most of them have no symmetries. So in dimension 3, every Curvature tensor is realized, right, by some local example. And I think most of these have no symmetries. I'm not sure anyone proves that. But I'm pretty sure that the FKM examples have no or only finite symmetry.
these seem like really interesting examples. Are there other questions? No, thank you again. Really nice talk.
Thank you for listening.
And